In this video, we will continue our investigation into the integral test. Let's just start off with a reminder of what the integral test tells us. If we let f be the function associated to the sequence we are summing up, and f happens to be continuous, positive, and decreasing, and noting that those hypotheses are satisfied are very important. Without them, we cannot apply the integral test. So with the hypotheses satisfied, the integral test tells us that the series we are interested in converges or diverges if and only if the associated improper integral converges or diverges. Let's look at one last example involved using the test. Let's use the integral test to determine whether the series given here converges or diverges, and we're going to see this as a slightly more involved example. So the associated function we have is f of x equals x e to the minus x, which we can maybe slightly more conveniently express as x e to the x. And what we need to do is note that the hypotheses are satisfied. That is, this function is continuous, positive, and decreasing on an interval from 1 to infinity. The fact that it's continuous and positive, we get immediately. So this function is certainly continuous and positive on the interval from 1 to infinity. Now for the decreasing portion, I don't think this is as obvious. The reason being is if you think about plugging in bigger numbers, x is getting bigger, so is e to the x, so it wouldn't be clear that the overall function is getting smaller, i.e. decreasing. So what we need to do for decreasing is calculate the derivative. So f prime x, we're going to just go ahead and use the quotient rule. So low d high minus high d low all over low squared. Note each and every term involves an e to the x, so we can pull an e to the x out of the top, out of the bottom, cancel. So that would be 1 minus x all over e to the x. And what we would like to know is where will this first derivative be negative? So this will be less than 0. And note this is the question we're asking, when is it negative? So whenever, well let's see here, e to the x is positive, so whenever 1 minus x is negative. That is whenever x is bigger than 1. So when x is bigger than 1. So what that tells us is that f is decreasing on the interval open at 1 to infinity. Now, as a side note, you might be concerned that it's only from an open interval at 1 to infinity. But really, all we need is that the function would be eventually decreasing. If there is some number here, 2, 3, 10, 100, and from that number on to infinity it's decreasing, that is what we would need. And the language we would use is, eventually decreasing. So because our associated function is continuous, positive, and decreasing, we can use the integral test. Let's do so. So for the integral test, what we need to do is evaluate the integral from 1 to infinity of the function x e to the minus x. And the convergence or divergence of this integral is going to imply the associated convergence or divergence of the series. Because it's an improper integral, our first step is to simply rewrite as a limit. And in order to evaluate this integral, I'm just going to remind you that when we see this form x e to the minus x, this is something that would imply an integration by parts, a polynomial multiplied by an exponential. So to the side, I'm going to simply evaluate the associated indefinite integral. So if we had x e to the minus x, we would let u be equal to x and dv be e to the minus x. So v would be minus e to the minus x, and du is dx. Integration by parts tells us uv minus the integral of v to u. So this becomes minus x e to the minus x minus, and then it's going to be in turn a minus the integral of e to the minus x. So we end up with minus x e to the minus x minus e to the minus x plus c. So doing this bit of work to the side, we find that for the improper integral, we have the limit as a goes to infinity, and we have the indefinite integral of x e to the minus x. So that would be minus x e to the minus x minus e to the minus x, and we're evaluating from 1 to a. So we plug in x equals a, so that would be minus a e to the minus a minus e to the minus a, and when you plug in x equals 1, you will have minus 1 e to the minus 1 minus e to the minus 1. So we have minus 2 e to the minus 1, which becomes minus a minus, so plus 2e to the minus 1. And now when we take the limit as a approaches infinity, note that for this e to the minus a term, that is going to go to 0. The 2e to the minus 1, that's a constant, so it's just going to go to that constant, and we'll write that as 2 over e. Now this remaining first part, minus a over e to the minus a, I'm going to rewrite this slightly. So this is the limit as a goes to infinity, minus a over e to the a, and then we're going to have plus the 2 over e. And note, if we look at this first limit as a goes to infinity, so does e to the a. So what we can do is apply L'Hopital's rule. So using L'Hopital's rule, this is the limit as a approaches infinity of minus 1 over e to the a plus the 2 over e that we have. The limit is now 0 plus 2 over e. So the improper integral converges to the number 2 over e. Therefore, by the integral test, that associated series, the sum from k equals 1 to infinity, ke to the minus k, converges. And as seen here, the examples can certainly be more involved. In this case, we had to use a derivative to see that the function was decreasing so that we could apply the integral test. And then for the associated integral, we had to use an advanced technique, here just integration by parts, but that resulting limits even required a L'Hopital's rule. So we do have to reach back to some of these techniques and tools that we've learned earlier this semester.